This lecture, I will discuss the Laplace transforms of step functions. Step functions are functions that have different formulas on different intervals of the independent variable. The simplest step functions are unit step functions. These functions are also called Heaviside functions. Let C be a positive number, and we define u sub c of x to be like this. 0 for x between 0 c and 1 for x greater than or equal to c. So the graph of such a UC looks like this. We have the x and then the value 0, 1, and c is somewhere here. Between 0 and c, the function is 0. So the graph is on the x-axis and 0 is included. We have the solid circle there. Then as c is not included, we have an empty circle. And starting at x equal to c and beyond, the function is 1. So the graph is a horizontal line as 1. This is u c of x. Let's compute the Laplace transform of such a function using the integral definition. The Laplace transform of ucx. As usual, we have integral from 0 to infinity of uc of x e to the minus s times x dx. Because a function ucx has different formulas, so we need to break into two intervals from 0 to c of the function plus integral from c to infinity. Now on the first interval from 0 to c, the function uc0, so it will not contribute to the integral, and we only have integral from c to infinity, and for that interval uc is 1. We have 1 e to the minus s times x dx. And as before, we will look at the limit a go to infinity, integral from c to a of e to the minus s times x dx. Using the antiderivative, we have limit a go to infinity and then e to the minus s times x divided by minus s. Here x go from c to a. Plug in value, limit a go to infinity of e to the minus s times a over minus s and minus e to the minus s times c over minus s. And we need to take this limit when a approaches positive infinity. So as before, we will assume that s is positive, so the limit of e to the minus s times a when a go to infinity equal to 0. And then if this happens, then we see that we get the Laplace transform of UCX is the first term is 0 and the second term we have minus become plus, and then on top we have e to the minus s times c. We usually write a constant first. I will write e to the minus c times s or divided by s. This is the Laplace transform of the unit step function. This formula will be provided in this table of Laplace transform. Now, in order to calculate the Laplace transform of more interesting or more complicated functions, we need to use another formula. So this relates with the so-called the cutoff of a function. So given a function g of x and a number c positive, so like this, we have the function g of x with the graph like this, and then a positive number c, yeah, the cutoff of the function is that we kind of like remove the first piece and replace by a horizontal segment between 0 and c, and the horizontal segment is on the x-axis, and we call the new function the cutoff of the original function g of x, and the formula is given by gx times uc of x. Remember that uc of x is 0 between 0 and c, and that's why we have the horizontal segment, and then uc of x is 1 from c and beyond, so it doesn't change the graph at all. Okay, so this second piece of the graph doesn't change, we only change the first piece. So the question is, what is the Laplace transform of the cutoff function gx times uc of x? Well, of course, the Laplace transform depends on what function g we have. Right? So we'll look at the formula that relate this Laplace transform with the Laplace transform of a function g. Laplace transform of something related with g here. Okay. So to obtain the formula, let's look at the definition of the Laplace transform. So Laplace transform of gx ucx is integral from 0 to infinity of gx ucx e to the minus s times x dx. As before, the function is 0 between 0 and c, so that will not contribute to the integral. Instead, we only have integral from c to infinity. And on that interval, the function ucx here, this factor here is 1. So we only have gx e to the minus s times x dx. Now to deal with this integral, we're gonna use a substitution. in calculus 1, you usually use u for substitution, but for this calculation, instead of using u, we're gonna use something else, like say t here, and the substitution is t equal to x plus c, sorry, x minus c. See, and so we have dt is the same as dx, and x is t plus c. So with substitution, the integral, originally the integral goes from c to infinity. That's what x is. But what about t? T is x minus c. So t would go from 0 to infinity minus c is still infinity. And then g of, now x is t plus c. So we have t plus c here. Then e to the minus s times t plus c. And dx is the same as dt. Now we're gonna do an algebra that distributes the s into the sum. We have e to the minus s times t, then minus s times c dt. For the exponential function, we split as e to the minus s times t times e to the minus s times c dt. The reason that I wanted to split the exponential into the product is because e minus s times c here is independent of t. It's a constant. We might take it out. And as usual, we're gonna write c first, so e to the minus cs instead of sc over there. And the integral from 0 to infinity of g of t plus c e to the minus st dt. Now, in order to have a formula, we're gonna do one more step. In the integral, the variable is t, but we know from calculus 1 that for definite integral, it doesn't matter what name of the independent variable we're using, because after all, it will just give us a number, right, independent of the variable we are integrating. So instead of t, we can go back to x, g x plus c and e to the minus s times x dx here. Now it's clearer. This formula, if you recall, is nothing but the formula, the integral formula for the Laplace transform of g of x plus c. The Laplace transform of whatever factor we have here. And in this case, it is x, g of x plus c. G of x plus c means that we change the input x to the new input x plus c. If you recall from college algebra, this is actually the shift of g to the left c units. Okay, so when we change the input from x to x plus c, we actually shift the graph c unit to the left. So let me summarize the formula that we will need to use later on. The Laplace transform of the cutoff function g of x ucx is e to the minus c times s times Laplace transform of the shift of g. g of x plus c. But keeping in mind that we don't use the original function here, we have to shift that c unit to the left. Now let's look at a few examples how to use the above formulas. Example 1. Find the Laplace transform of the function f of x with several formula here. Let's say 1 for x between 0 and 3, and then -1 x between 3 and 4, and lastly 2 for x bigger than equal to 4. This is a piecewise defined function or step functions. It has 3 different formulas. Now we may be able to use the integral definition to compute the Laplace transform. But instead of computing 3 integrals, we can apply the formula. But in order to use the formula, we have to rewrite the function fx as a single expression using step functions, using unit step functions. And here's how we do it. We have f of x equals to, the very first formula is 1. We begin with that 1 plus. Now in the definition of the function, there is a change when we go beyond 3, right? Between 0 and 3, we have the first formula, but then beyond 3, we have a new formula, and then beyond 4, we have a different formula as well. Because of that reason, we will need to have 2 unit step functions. The first one is u3x with a certain factor in front. And the factor here is the difference between the 2 formula. When we go from the first interval to the second interval at x equal to 3, we change from 1 to -1. So the difference of the formula is -1 minus 1. This is the difference. -1 subtract 1. Similarly, at 4 and beyond, we need to use u4, and the difference between the previous formula and the next formula, when we jump when we pass 4, is 2 minus -1. The difference in the formula, again 2 minus -1. Yeah, difference. Now we just need to simplify. We get 1, and then minus 1 with a -2 times of u3 x plus 3 u4 x. Now we have a single formula for the function f. Then we apply the Laplace transform. By the linearity, we can split the Laplace transform into several pieces. So Laplace transform 1 minus twice Laplace transform of u3 plus 3 Laplace transform of u4x. Laplace transform of 1 is 1 over s minus 2 times Laplace transform of u3. There's a formula which says that Laplace transform of uc is e to the minus cs, so minus 3s divided by s. So here we use c equal to 3, and the next one we will have c equal to 4 plus 3 e to the minus 4s divided by s, and this is the Laplace transform of the given step functions. Now let us look at another example, a little bit more difficult example. Example 2. Find the Laplace transform of function f given by 0 for x between 0 and 2, and then x squared for x bigger than or equal to 2. We have two different formula, 0 first and then x squared. So as before, we will rewrite the function using a single formula. We begin with 0 plus. Here, there's only one change in the formula, which happens at 2 and then beyond. So we need to use u sub 2 of x. What is the difference between the two formulas? The first formula is 0, and the second formula, when we change to 2 and beyond, is x squared. The difference is just x squared minus 0. So basically the function is x squared times u2 of x, a simple formula. So the Laplace transform of f of x is the Laplace transform of this x squared times u2x. Right? Laplace transform of function times a unit step function. This we need to use the formula for the cutoff function here. So how does the formula say? What does it say? Let's go back here. Laplace transform of the cutoff gx times ucx. First, we have e to the minus cs, and then we have Laplace transform of this shift. This function is not the same as the original gx, but it's the shift, meaning that the input is changed to x plus c. Whenever we have the input x, we need to replace that by x plus c. Over here, c equal to 2. So the formula says we have e to the minus cs minus 2s times Laplace transform of a new function. The original function is x squared. So the new function will be x plus c squared, meaning x plus 2 squared. So you need to be very careful when writing down the shift of the function, shift to the left. And once we have that, we can distribute to get x squared plus 4x plus 4, and then we use the linearity of the Laplace transform, e to the minus 2s times Laplace transform of x squared plus 4 Laplace transform of x plus Laplace transform of the constant 4. Now look at the table of Laplace transform and write down the answer. Laplace transform of x squared turns out to be 2 over s cubed plus 4 times Laplace transform of x is 1 over s squared. And lastly, Laplace transform of constant is just a constant over s. We have obtained the answer for the Laplace transform of the given problem. Now let's look at another example. Example 3. Find the Laplace transform. In this example, we have three formulas for the function. X for x between 0 and 1, and then we have 3x plus 1 for x between 1 and 4, and lastly we get 2 for x bigger than or equal to 4. In order to compute the Laplace transform of this function, we will rewrite fx using step functions, using unit step functions. We begin with the first formula, which is x here. And then for the formulas, change from x to 3x plus 1 when we pass through 1, when x go past 1. So we need to use u1 of x. And the factor in front is the difference between the two formulas. The new formula is 3x plus 1, and the previous one is x. So I need to subtract the two formulas to get that. And then we also have u4 of x. The new formula is 2, subtract the previous formula in parentheses 3x plus 1. Let's simplify. We have 2x plus 1 times u1 of x plus this, we distribute the minus sign. Don't forget the parentheses, so we can distribute the minus sign, get minus 3x, and then plus 1 times u4x. Now let's compute the Laplace transform. By the linearity of the Laplace transform, we split into Laplace transform of x plus Laplace transform of the cutoff 2x plus 1 times u1x plus Laplace transform of minus 3x plus 1 times u4x. This is another cutoff function. But for the first one, we have c is 1 here, uc, u1, and c for the second 4. Now we know that the Laplace transform of x is 1 over s squared. And then by the formula for the Laplace transform of the cutoff function, we have e to the minus c s. C is 1, so e to the minus s times Laplace transform of the shift. The shift is that whenever we have x, we have to replace by x plus c, which means x plus 1 here. So we have 2 times x replaced by x plus 1, and then we have plus 1 at the end already. Similarly, for the second Laplace transform of the cutoff function, we have e to the minus cs, which is for s, Laplace transform of, this time we replace x by x plus 4, so minus 3 times x plus 4, and then add 1 at the end, which give us 1 over s squared plus e to the minus s Laplace transform of 2x plus 3 plus e to the minus 4s Laplace transform of, simplify this, minus 3x minus 12 plus 1 give us minus 11. Now using the linearity and the formula for Laplace transform, we have e to the minus s times here Laplace transform of 2x is 2 Laplace transform of x, which is s squared, 1 over s squared, so 2 over s squared, and then Laplace transform 3 is 3 over s, plus e to the minus 4s times Laplace transform of minus 3x give us minus 3 over s squared, and then minus 11 over s. So we have obtained the answer, the Laplace transform of the piecewise defined function. Now you don't need to simplify more, you can leave it like this. Now using the formula for the Laplace transform of the cutoff function, we can derive another formula or something related with, but different. We call this a shift of a function. So what happens is that we have a graph of a function f like this, and we have a positive number c here. As before, it gives us a point on the graph. Now, but what we do here is different from before. Before we cut off, so we remove the first piece and replace by horizontal segment. Here we don't do that. Instead, we shift the entire graph to the right hand side, 3 units to the right hand side. So what means that the first point becomes a new point right here. We shift it. So I should shift everything, move everything C unit. This top point right here will move to the top point there, but again, C unit to the right. C unit to the right. But then we have the gap between 0 and C. We replace it by a line segment. So the formula for the shift is given by this. F of x minus c times uc. The formula for the Laplace transform looks like this. Laplace transform of f of x minus c uc x is we can make use of the formula for the cutoff. The answer is e to the minus c times s times the Laplace transform. This piece is the shift f of x minus c. We have e to the minus cs times Laplace transform of this piece shift to the left c unit. But when we shift the entire new piece here to the left c unit, we get back to exactly the function f. So right here, we only have f of x. That's before this formula will be given in the table of Laplace transform as well. However, this will be given in the format of inverse Laplace transform. We need to use this formula for inverse Laplace transform in order to solve differential equations with step functions. That will be discussed in the next topic. And this is the end of the lecture today.